So let's try the following experiment. Let's say that we have a box sliding along, mass m, moving at vi, and now there is going to be some friction here between the box and the surface, and we'll give it a value of mu k. After some distance, delta x, the box comes to rest. Okay, push this box along the ground, it's going to slide along, and eventually it's going to come to rest. Let's give you some numbers to work with, and then we'll figure out what delta x is. So let's say that the mass is 2 kilograms. We'll say that VI is 10 meters per second. We'll say that mu k is 0.5. Vf is 0. And we want to find that distance, delta x. So how can we do this? How can we deal with this problem? Somebody give me a thought. What's that? Maybe the kinematic equations, but we're in a different chapter now. So maybe the chapter that we're in has some stuff that is relevant to this. Okay, you said the change in kinetic energy. What about the change in kinetic energy? It equals work, right? This is the work kinetic energy theorem. If I'm going to work on the box, I can change its kinetic energy. We know what changing kinetic energy is. It's just 1/2 m Vf squared minus 1/2 m Vi squared. What about work? What do I do with this? What is doing the work on the box as it slides? Yeah, friction due to that coefficient, mu k. So as the box is moving along, there's actually a force back to the left of magnitude F sub k, kinetic friction, right? Box is sliding along, friction is trying to slow it down. Okay. So what do I do? How do I calculate work due to friction? We know that work is the integral of f dot dx, which is f sub k, cosine of the angle between the two. What's that angle that I want to put in there? Well, delta x is to the right. It's the displacement. It moved to the right. F sub k is to the left. So what's the angle between F sub k and delta x? 180. 180, take the cosine of that, you get a -1. So this whole thing becomes negative integral of fk dx. Fk is constant the whole way, and so this whole thing just becomes Fk delta x. All right, so we can put that up here in our equation. This has to equal negative F sub k times delta x. And now we should be able to take this and solve for delta x. Let's rewrite it. And we'll go with, how about yellow? All right, so this equation becomes the following. 1/2 m Vf squared minus 1/2 m Vi squared equals negative F sub k delta x. But Vf is 0. We can get rid of that one. The negative signs go away, and I can quickly solve this for delta x. Delta x equals 1/2 m Vi squared divided by f sub k. Do we have all those numbers? We have m, right? We have vi. We don't really have f sub k yet. So we need to figure out what f sub k is. How do we do that? Anybody remember what f sub k is? F sub k equals mu k times n. But if we're on a horizontal surface, what is n? It's just the weight of the object, right? So this becomes mu k times m times g. And so now that I can put into here, and we get 1/2 m vi squared divided by mu k mg. The m's drop out, and we get vi squared divided by 2 mu k times g. So again, when you get these answers, take a look at them. See if they make sense. This says that delta x is going to go like these quantities. If I push this box faster, should it slide farther? Yeah, that makes sense, right? Vi increases, delta x will increase. If I make the surface really slippery, like ice, then mu k goes down. Since it's in the denominator, that makes delta x go up. That also makes sense, right? If mu k gets really big, like rubber on concrete, this thing isn't going to slide as far. So those things make sense. It's sort of surprising that the mass drops out, right? It says if I do a big heavy box or a small box, and I push them at the same vi, they're going to slide the same distance, which is a little bit counterintuitive, right? Because the big box is certainly heavier, will certainly have a bigger f sub k, but it also has more mass that it's trying to slow down, and those two things exactly balance out. So it's mass independent, which is kind of cool. What about this g? We have a g sitting down here, and yet everything was horizontal, right? Usually when we think about g, we're thinking about the acceleration due to gravity, not something that relates to horizontal motion. Why is g down there? Let me phrase the question a different way. And everybody turn on your mics and let's have a little chat about this. Push your mic button. First off, let's say hello to everybody at home on 3. Ready? 1, 2, 3. Hello.
Hello.
Anybody you want to say shout out to? Just go ahead.
Shout out to Steve-O.
You don't even know.
Again to Steve-O? Is this like Jackass Steve-O, or is this an actual person in the... Okay. All right. When G is sitting right here, what does this tell us if we tried this experiment not on the Earth, but on the moon? If I did this on the moon, would the box slide farther? Table 3 back there, you guys are nodding your heads. Tell me why.
Because G would be smaller, so to make them a little bigger.
Yeah, because G is sort of the acceleration due to gravity on the Earth. But on the moon, we know that gravity is smaller, and so the acceleration due to gravity is smaller. And so it would slide farther. That's totally a good way to think about it. Think about the box on the table, right? It sort of sinks into the table. And the more I can have it sink in, the more it's going to grab hold as it slides, and the better it will stop. But if I go to the moon, where it's not really digging into the table, it's going to slide a lot farther. And in fact, if G goes to 0, like there's no gravity, then the thing will just slide forever. Doesn't really even care that it's on a table, it'll just float away. All right, so that seems to make sense. Let's, you guys can turn your mics back off. I know you like the privacy over there. Let's plug in the numbers and see what we get. So VI was 10 squared And seriously, when your mics are off, you can say just about anything you want over there. Nobody's going to hear you because the only mic is right here. Really? Is that what you're going to talk about? 2 times 0.5 times 9.8. Somebody can punch that into your calculator and figure out what it is. I'm going to say it's about 100 over 9.8, which is pretty close to 10. Okay, 10 meters. That's how far this thing would slide with those given numbers.